So welcome to this live interview. Today we have the pleasure of talking to Iskander Umarov, who's a technical director at TrueSoft, who work on artificial contender, which is a middleware technology for behavior capture. So welcome, Iskander.
Hi. Hi, everyone.
So Iskander works for TrueSoft, and TrueSoft is a sponsor of AIGameDev.com, so this is technically a sponsored seminar. Um, But yeah, I'm particularly looking forward to it. So don't let that fool you, because we're going to talk about lots of cool technology today. And Iskander and artificial contender is one of the most well developed, or even the most developed behavior capture system in the world probably, and it's one of the only ones that's been applied in industry multiple times. So it's going to be a very enlightening process. So if you have any questions, feel free to post them. This is the rough outline for the presentation. We'll take questions that fit into this structure as we go along. But if you have any questions that don't quite fit, I'll leave them until the end and then we can discuss it in a bit more detail. So, do you want to get going, Iskander?
All right, all right. So, in this presentation, I'll talk about behavior capture AI in general and about its implementation in the artificial contender technology. We'll talk about what behavior capture AI brings to the game developers and gamers. I'll also briefly cover similarities and differences between our technology and other research. I'll provide some technical details on artificial contender using football, soccer game as an example.
Mm-hmm.
So yeah, let's go to the next slide. All right, so with behavior capture AI, game characters can be trained by simply playing the game. Uh, Another possibility is capturing data from the real world. So basically, right now, everything we did before and everything you can find in a public research usually is about capturing data from a game controller mouse, basically from a game player. But in the future, the same concept should allow capturing data from, let's say, real athletes on a football field or something like that. The term behavior capture for AI is derived from a term motion capture for graphics. Because of the similar concept, real humans are used as models for game agents. And we believe that behavior capture AI is a natural next step in industrial AI methods.
I'd like to ask you generally, who thinks that let's say behavior capture is a good idea versus who doesn't. And it seems to me like designers are really keen on the idea, whereas maybe technical people might be a bit less. So what's your experience been on that? Who thinks it's the next step and who's a bit more reluctant?
Well, I think generally everybody I talk about this, every single person who attended presentation, everybody like tend to think that it is a good idea, that it is a natural next step. The skepticism usually comes from, I'd say, if it wasn't a ready-to-use solution, there is a skepticism on whether it actually can be done. And also there are questions about how easy it is to use in a real game development workflow.
Mhm.
Like how do you actually apply the technology to actual game, and what would the process look like?
Yeah, but I agree on the promise. I think it definitely is something to look into, especially as handcrafted solutions don't scale. And yeah, there was an interesting quote from Will Wright a few months ago at the GDC, and he said that the future is being able to crowdsource all the AI algorithms and let all the players actually take part in the creation of the behavior. And so this seems like a great way to do it.
Yes, yes, and we'll definitely talk more about this, about what questions developers ask and how it could be used, things like that. So, main keywords. So I spoke about what behavior capture AI is, and this slides basically lists the keywords that are like related to the term behavior capture. Like if you look for any of those, like learning from observation or imitation learning or behavioral cloning, you'll be able to find a related research on the area. To summarize, if someone is interested in this research, they should like look through all these keywords, and
Hmm.
there are many. All right, and the secondary keywords, they are related to the way we implemented the behavior capture AI in our technology. So we
Hmm.
utilize case-based reasoning, case-based planning, concepts behind goal-oriented action planning, and also reinforcement learning. So these two slides summarize all the keywords that are related to our presentation today.
Generally, it's been my, at least my, from my reading, that most of the behavior capture, imitation learning solutions fall into case-based reasoning. Is there anything else but case-based reasoning that applies here to this kind of problem?
Yes, definitely. There are other approaches. For example, one of the research I'm familiar with used Gaussian mixture models to create classifiers. So basically, classifier-based models
Hmm.
could be used for the same purpose. You can use decision trees and things like that.
Hmm.
Uh, I haven't seen like working implementations of neural networks for the same purpose, but I can imagine it could be done as well.
Right, so the general class of solution here we're talking about is pattern recognition, finding what the common pattern is in a series of data, and then extracting the useful action in this case. So any kind of pattern recognizer would be a potentially applicable solution. Do you think that's the case?
It could work, but our solution is definitely not a
Mm-hmm.
pattern recognition. We are a case-based reasoning system, memory-based system, so we don't recognize any patterns. But it could be, I think it could be possible to implement a system this way, even though I would not recommend doing it this way.
Mm-hmm. Now, I guess when people think about behavior capture and machine learning, they might not necessarily associate that kind of technology with, let's say, goal-oriented planning. Um, how does that fit into the actual the case-based reasoning, processing the data? How does the planning fit in with the that approach?
This is a good question. We use planning in non-traditional way. There'll be some slides where I'll cover planning in more details, but the overall idea is we use planning to try to preserve a sequence of actions that a
Mhm.
trainer did. So the planning's purpose in our case is to try to preserve a sequence. So it's a different goal comparing to what goal-oriented action planning, for example, used for.
So it seems like these two technologies are kind of complementary. Whereas you have, for instance, the behavior capture for, let's say, finding those human patterns and the subtle details of the human behavior within a game. And the planning would help make that goal oriented in all the possible cases so that your game doesn't break.
Yes, yes, something like that. So the goal is not to break the game. Yeah, that's good put. Well put.
Talk us through this slide then.
Yes. Well, as I said, you can find related research by using each of the keywords like learning by observation, imitation learning,
Hmm.
etc. You'll be able to find most research in machine learning, also some research in robotics. This slide lists a few examples that I think are the most relevant, and I'll talk about some differences and similarities between what we do and what others do several slides from now.
Hmm. Yeah, we'll post the references to these papers when we put the recording up online so you can find them. Um, but to what?
Sure, and I can provide more, by the way.
Oh, great, fantastic. And when actually, which of these is most similar to the solution that you ended up choosing, and which is the most different?
From the four that we have on a slide, let me take a look. Some concepts from learning from observation and practice using
Hmm.
primitives looks very similar in terms of trying to extract a high-level action. And the funny thing is, what we call high-level action, this paper calls primitive, but usually it's the same concept. Then let me see. The most different is probably the second paper. We don't use Gaussian mixture models or
Hmm.
classifiers in a way that this paper uses. RoboCop agent learning from observations is the most similar in terms of the current example. We'll be using a
Hmm.
football during this presentation.
Okay, so it seems like one of the biggest challenges, at least from looking just at the title of these the research, is to find the set of let's say the purpose of each action sequence. So here we have the goal, and here you mentioned primitives as high level actions. So the idea that you're trying to understand what was going on when these low level actions were being executed, is that the most difficult part of the problem?
It is one of the most difficult problems, but it's very much depend on the game. As you know, our forte right now are sports games, fighting games, action games, and for those types of games, this problem is not as difficult as, for example, real-time strategy
Hmm.
or some team-based shooters. So yes, it is a challenge, but it depends on a game very much how big this challenge is.
Okay, we're going to go into more detail about this over the next few slides, so we'll dig into this.
All right. So the question: what does behavior capture AI do for game developers? So most importantly, it has capabilities to provide better, more human-like agents for games. From the workflow perspective, it provides a way to approach AI development as a content design, and it allows game designers and subject matter experts to directly participate in the AI development, as opposed
Hmm.
to talking to engineers, then look at the result, and talk to engineers again. Uh, so fully working behavior capture AI solution should allow designers to work with the game in a similar way they work with level design.
Hmm.
And when you take a look at the second and third bullet, like together, they definitely provide a way to save time and money.
Hmm. I'm wondering to what extent using behavior capture would move your development time to a slightly different part of the problem. You'd spend a bit more time setting it up and building, let's say, a framework to capture your data and then create behaviors from it. Um, but that would scale up better. So I guess it's more a question of at least realizing where the time is being spent. I guess from my perspective, it seems like the whole workflow is a bit different.
Yeah, I need to provide a couple details. The saving, um, at least the most important saving, will come from the fact of that having a behavior capture AI solution will allow you to have a lot of variety
Hmm.
if you need to. So basically, if you game design document
Hmm.
have specifications for, let's say tens or hundreds of differently behaving agents, you will definitely save a lot of time and money if you have behavior capture AI, because once you put it in, then you can have designers and expert
Hmm.
gamers to train those varieties for you. But if you have a game where an agent's supposed to basically act the same all the time in all levels, and all the differences will only come from, let's say, differences in the environment, you won't have as much saving.
Hmm.
Does it make sense?
Yeah, that makes sense. Absolutely.
So, well, I guess the best example would be a football game, of course.
Hmm.
So you have hundreds of clubs, you have hundreds of national teams, and let's say you want to have different personalities for those. And if you have specifications for each of those teams, and then you need to implement it
Hmm.
the normal way without behavior capture, it'll be a tremendous achievement. But with the behavior capture AI, you just have those guys who claim they can play in
Hmm.
those styles, and you have them play in those styles, and you have a technology that capture those styles, and then you have your variety ready for you.
We have an interesting question by Baylor in the chat who says, uh, how do you define behavior? I mean, what are we capturing here? Are we talking about the low level behaviors, the tactics, the strategy? What level are we capturing behavior?
That's a very good question. We capturing behavior. Well, if we talk about our solution, we should every time the question like this comes, I'll try to answer it from both perspective of our
Hmm.
solution and perspective of behavior AI in general. So from our solution, we capture a low level behavior, but the behavior is organized in our system in a way allowing the tactical and strategical analysis on top of it.
Mm-hmm.
So the reason for it, our agent has to be able to act in the game. Like there is nothing between the actual game engine and the agent that would, let's say, translate a high level behavior that we captured and create some kind of a low level behavior
Mm-hmm.
based on it. Our agent's supposed to play the game. So we capture a low level behavior. If we talk football as an example, we capture actions as often as 5 to 7 times per
Mm-hmm.
second. So it's like really low level. But at the same time, these actions are assembled in the action sequences that you can look at tactics of a high level, or even a strategy of a high level, and we'll definitely talk about it later on. But if we
Mm-hmm.
talk about behavior capture AI in general, um, there are numerous papers um, that talk about a strategic element at the most. For example, you take a real-time strategy game, um, and then you capture a low-level behavior, but then you have someone who can annotate that behavior and annotate a series of low-level actions, annotate them with a high-level goal. And the big purpose for that research is to be able to recreate high level goals and high level behaviors from low level ones. So again, if we look at the research as a whole, there are different approaches that you can approach it: low level, medium level, high level. But we approach it on a low level. But in the system, we have capabilities to analyze tactics and
Mm-hmm.
strategies as well.
Okay, so for football, as an example, you meant every fifth of a second, you'd be capturing the relative movement, position. Do I pass the ball? Should I, what position should I be in? Should I tackle? So the basic actions of football would be what we're learning for each individual character in the game.
Yes.
Okay, I'm also wondering to what extent it makes sense to apply behavior capture to such symmetrical games. Let's say it doesn't necessarily have to be a sports game, but maybe like a capture the flag game where you have a very distinct um, team personality, which you wouldn't necessarily find in a single player game where you want to have maybe two or three variations of enemies, but in a very diverse multiplayer game where you want to have the second player being played by an AI that has style. It seems like behavior capture would be a great advantage here compared to other techniques.
Yeah, definitely, definitely. And I'll talk about advantages to the end users a couple of
Mm-hmm.
slides after this one. And one of the advantages that the end user gamer can get, if this technology is exposed to the gamer, then the gamer can train ally for himself.
Okay, yeah, this is the second slide for game developers.
Yes. So this slide, okay, so game developers can utilize behavior capture AI concept to either solve particular issues in AI, add new features to the game, or they can create AI system from the scratch. That's an important point. Like if there is a game that already has a big AI system in place, and let's say almost everything works,
Mm-hmm.
but there are some things that needs to get improved, it's possible to use a combination of two systems. Again, if we talk about football as an example, um, the team play, like other players, the players without the ball, handled by a regularized solution, and our technology handles only the player with the ball. So that's the example of a combination.
Mm-hmm. Mm-hmm. Yeah, it does seem like there's uh, in general, even not so much applying it to different characters in the game, but even parts of the AI. So if you have to make a specific decision about where the referee should be on the pitch, but all the rest of the logic is run through a state machine or a script, then you could combine within the same behavior, within the same character, like automatedly captured behavior plus the scripted solution. Is that the kind of stuff you've done already?
Yes, we did things like that. I can give an example from basketball game that which we didn't do, but that was some question about it. For example, you can have the whole game handled by a regular AI solution,
Mm-hmm.
and then only have star players star players controlled by behavior capture AI from time to time.
Hmm. And so, yeah, that seems another perfect application of behavior capture, just because you get that distinct personality, which would take a lot of time to tweak
Yes.
individually for each of the superstars. Yeah.
Yeah, absolutely. And as we noticed in our years talking to game developers, working with game developers, in every game development team there are at least a couple of designers who at least claim to know how what behavior should look like, and they usually can take a controller and show
Hmm.
it. So that's where behavior capture AI is like the best fit. If you have a person who can show it with the controller in hand, that's everything you need.
Okay. So the advantage for players, there's quite a few.
Yes, if behavior capture AI agents are built in a game, what gamers get? Gamers get convincing, again, more human-like opponents and allies. They got tremendous amount of variety to play with, play against. They get trainability. By trainability, I mean they get an option, if game developers allow them, they get an option to train something in the game. Let's say they can train their own teams, they can train their own
Hmm.
teammates, sparring partners, or let's say participate in some kind of a online tournament where only bots play and those bots are trained by human users instead of
Hmm.
programmed, things like that. And adaptability. Adaptability itself is not like a built-in feature for every behavior capture AI solution, but this is what we found, at least for our solution, is very natural. The way the data is usually structured in memory-based solutions allow applying reinforcement learning or our machine learning techniques
Hmm.
to allow agents to adapt for one or another reason, and it could be turned on and off.
Okay, so that's where you mentioned, for example, planning, goal-oriented planning, and reinforcement learning earlier. I guess that would be the two key components that make the final results more adaptive.
Yes, yes, but I should note again that in our solution, planning is used to preserve sequences, and reinforcement learning is used to provide agents with the ability to adapt. And those two techniques combine in an interesting way, where like goal-oriented planning try to preserve sequences, but at the same time, certain actions are giving priorities based on previous reinforcement learning step.
Hmm. Okay, so I guess you must be getting quite a few questions about your solutions when you talk to different developers. So could you talk us through them?
Oh yes, a lot. Oh yes, yeah. So yeah, these are two slides about the questions, and I try to list only what I think the most important, what most frequently asked questions about behavior capture AI, how it can be applied, how it can actually be used. So let's go through those. So first, okay, you have a behavior capture AI solution. How would you actually train AI agents to achieve desired behavior? How would you provide designers with a high level of control? What I noticed myself, that sometimes you can have a producer and several game designers. Producer has an overall idea of what he wants to achieve, and designers somehow have to be able to bring those ideas to life.
Hmm.
And in a usual workflow, designers would, well, talk to engineers, and engineers talk back to game designers. Producers will look at the overall result. With our solution, it's also not like very similar to kind of translate ideas that producer have to designers that have controllers in their hands. So um, it's still a question. So after you train it, train agents, how would you modify the behaviors? How would you say, again, producer or head game designer, look at the agent play and say, okay, I don't like this action, I don't like this behavior. How would you remove unwanted behaviors? How would you add missing behaviors? How would you provide alternative behaviors for behaviors that designers or producers didn't like? Then other questions, how would you train robust agents? By robust, I mean avoid undertraining, avoid overtraining. How would you measure
Hmm.
all of this?
Yeah, but it seems to me that the biggest issues I've heard, at least not with behavior capture, but machine learning in general, is this one in the middle here, the idea of having control over what you're creating. I guess that's a challenge because in a way you have to give up a little bit of control to get all the benefits out of it. So is the solution more of a design solution than a technical one, for instance?
Can you repeat the question,
Yeah.
or it was just a comment?
No, well, I'm just curious if
Okay.
these issues that people are having with behavior capture, for instance, they're more of let's say a people have done things in a certain way for the past 10 years and they can't wrap their heads around the idea that they might not have minute low level control over each individual action, and that's some trouble that people had switching to planners, is that you can't easily tweak what's going on under the hood, and so there are many studios that have objections with planners, and it seems like it's the same kind of methodology objection here, and it
Yes.
seems like training people to understand this question from the design perspective is almost more important than providing solid technology for the game developers.
Yeah, 100%. I 100% agree to your comment. And what we've done, we try to listen as much as we can to producers, to designers, and try to adapt the technology, change it, provide a tool set. And this is where I'll mention the tool set for the first time. Like if you have a powerful tool set behind the technology that allow tweaking everything a designer wants to tweak,
Mm-hmm.
and provide him with an easy way to do it, to understand, that's basically an answer to this question.
Mm-hmm. Okay, let's move on.
These are the more in-depth questions that are usually asked after, let's say, like second or first round of presentations,
Mm-hmm.
technical analysis. Okay, you answered all your questions about how do you remove unwanted behaviors, how you have control. Now, how would you improve agent's performance without changing the playing style? Again, you have a designer, he trained a certain agent, he spent, let's say, an hour training, and everything likes the way it looks, but then during QA, someone says, okay, it looks good, but it's too weak. So what do? You have a designer to retrain it again, or should be another way? So I will, of course, talk about it again, a few slides from this one, but the answer that we found was reinforcement learning. So you apply reinforcement learning on top of the existing style, and you have your answer. Now, the second question on the same slide, how would you increase, decrease difficulty levels? Now, how would you provide a flexible workflow for development of agents? And
Mm-hmm.
by flexible workflow, I mean, okay, you have level designers, you have all your artists, you have audio, you have the whole development pipeline where behavior capture solution should be placed in, like where it's at place, and when in the development you can actually start developing
Mm-hmm.
agents, what happens if you change the game engine after you train some agents, like things like that. And then the last two questions, they related to others, of course, but how would you avoid
Mm-hmm.
a black box issue? Like, okay, there are certain things under the hood, you want to tweak some things, and how would you avoid this sense that at a certain level you are facing a black box and you can't do anything? Um, and the most like tricky question in terms of let's say depth, or a depth of the question, is how would you find a balance between reactive behaviors and a plan? And again, especially if someone in the audience is interested, we'll get into more details. But
Mm-hmm.
what I personally noticed when I talk about planning too much, audience becomes concerned with how reactive agents are. Let's say, okay, I say we plan this, we plan that, we'll look,
Mm-hmm.
let's say 5 seconds ahead or 2 minutes ahead, and now we have a plan, and then people immediately think, okay, if you're playing that far, how could you be reactive enough? In a football game, everything can
Yeah.
change like every second or so. Okay, then I adjust my speech, and I concentrate on the fact that our behavior capture agents make new decisions 5 times per second, and now we face a skepticism about, okay, it's the system is too reactive. It just reacts to things. It doesn't plan anything. So in reality, we have a complex combination of where the designer or knowledge engineer can tweak a system in a way allowing it to find a sweet spot by how,
Mm-hmm.
how often it should replan and how rigid those plans supposed to be. And that's an interesting point in itself, because by having this parameter, you can have certain kind of sub characters created on the same train style. Let's say Alex would train an Austria football team to
Hmm.
play, and then we have a certain substyles based on the rigidness of the plan. Let's say, okay, substyle number one should be as rigid as possible and should not replan anything except it's absolutely necessary.
Hmm.
But substyle number two should be very flexible and try to replan everything 5 times a second.
I don't think using the Austrian football team is a great example, but um, uh, generally, I want to also mention the black box issue. It seems to me that's also a psychological issue as well. I mean, I've worked with many white box systems, or at least systems where you can get inside and change everything, and those systems get so complex that it's it's worse than a black box. So I think that developers will have to become a bit more comfortable with the idea of just saying this is a nice small isolated problem, solve it, and you just give it to an AI technique. It could be behavior capture, it could be planning, it could be machine learning of any kind. And so I think this is also a psychological thing that comes from our background over the last 10, 20 years, that we've had simple systems to deal with. But as we start increasing the complexity, we're going to have to face the facts that we can't, break down into every little detail. So I guess the same comment that I had on the previous
Agree.
slide about this.
Yes. Yes.
Okay, so tell us more how you approach this then with the artificial contender. First, tell us briefly what artificial contender is.
Yes. So, next several slides will provide a brief description of our behavior capture array solution that we call artificial contender. I will explain main elements of the technology, and I will provide some examples based on games we worked on. So again, artificial contender is an AI technology. It's AI middleware that is already applied on PC, PlayStation 2, Xbox 360, and PlayStation 3, and it is a powerful set of AI tools that run under Windows. Those tools can communicate with each other, and some of those tools are game independent. Some of the tools are very game dependent and configurable.
Okay, so this is the meat of the technology. Tell us how it works.
This slide and the next slide, they do not explain like exactly how the technology work step by step, but here I try to reference again relevant
Hmm.
keywords, relevant terms, and how it works again in terms of relevant research. So we use case-based reasoning, we used case-based planning. Both topics have not been invented by ourselves, but we definitely have our own input to both of those.
Hmm.
Um, for case-based reasoning, we have our own method for representing, storing, and retrieving knowledge, cases, or some people call it episodic knowledge base.
Hmm.
We use semantic directed graphs as a kind of a low-level representation for the knowledge. We call those graphs acting graphs. Um, Going back to the question that somebody asked about how low level a behavior is, those semantic directed graphs are very, very, very low level. Then we have generalization trees. In some cases, they are like more generalization graphs, but the idea is they built on top of the low-level action graph, and those generalization structures provide means for fast, real-time generalization. And it's, of course, vital for every case-based reasoning system to be able to find relevant cases to the case you're looking at
Hmm.
right now. And then in our system, the knowledge organized hierarchy in a hierarchical way, allowing tactical and strategic analysis. And game situation and action representation are, of course, game dependent and very much flexible.
Hmm.
So you don't have to, like for every application, you don't have to fit your data in some rigid structure. You basically have flexibility to have a very different representation depending on what kind of game you're working on. And then the third cornerstone for our technology is a generic programming approach that we use for handling algorithmic complexity in decision-making module.
Mm-hmm.
And algorithmic complexity, it doesn't come from the fact that we try to create some kind of an algorithm for every single game, but algorithmic complexity comes from the fact that we need to somehow create the knowledge processing conveyor that uses knowledge representation on different levels of
Mm-hmm.
abstraction, then feed it through filtering system that analyzes action, then feed it through the planner, etc., etc. And the method that we used got recently published in Game Programming Gems 7. So if someone is interested, it's an interesting approach of how to apply
Mm-hmm.
templates and generic programming to to algorithmic complexity.
Okay, I think we we could use a quick example of let's say these different terms in the context of a football game. I think that might help explain. Do you want to go through this now, or shall we wait until a little bit later?
Let's see. Let's do it later because we have some pictures
Okay.
for graphs and some structural representation for knowledge and the decision-making conveyor, like 5 or 7 slides from now.
Mm-hmm.
Okay, then the next slide also explains technologies behind our middleware. So we also have the optional reinforcement learning module that allows to agents to be adaptable. And again, I'll stress the point that adaptability could be used for both creating more challenging opponents or less challenging ones, if that's the
Mm-hmm.
goal in your design document, or if that's what you're working on. Let's say you have your style and now you want to make it less
Mm-hmm.
challenging for the user, and you can use reinforcement learning for that as well. Now, the system could be configured either as passive or active learning system. It could be configured as unsupervised or supervised learning system.
Mm-hmm.
And it has a powerful set of tools that allow a maximum level of control. And this level of control, going back to Alex, your comment, basically our tool set could be divided in 3 layers. One layer AI developers will use. Next layer every person with like reasonable engineering background can use, and the third layer every game designer can use. And if someone is interested to talk more about passive, active, unsupervised, supervised, we can do it a little bit later.
Yeah, I was just thinking if we could just give a quick example. Is active learning the process of learning within the game? Is that online learning?
Yeah, the idea is this: if you have an agent that can explore its environment on
Mm-hmm.
its own, makes its own decisions and learn from them, you will have an active learning system.
Okay.
If
Yeah.
you have an agent that, let's say, trained by someone and you can't go beyond the boundaries of
Mm-hmm.
what was trained, you will have a passive learning system. And with the combination of case-based reasoning, case-based planning, with reinforcement learning, you can have active learning system. Without it, you will have a passive learning system.
Mm-hmm. Okay, so it's the idea that at any particular situation, if I always pick the best option, then I'm not exploring alternatives and I'm not exploring the space of possibilities. So I will always end up picking the best option. Whereas if 20% of the time I pick a random behavior and then compare how that did to the previous situation, then that becomes, yeah, active learning. I guess that's something that's talked about in.
Yes, referencing what we talked about, like questions that designers would ask, some
Mm-hmm.
issues that producers might have with active learning systems. The usual issue is after you release the game, it's kind of a scary to have something very unpredictable out there. So active learning system could be a scary point, but for some games it could be the right solution. Another possible way to use an active learning system is to, let's say, I train a boxer in a boxer game, and then I will have this boxer to play against every other boxer that we trained before during the
Mm-hmm.
nighttime, and then I come in the morning and I'll see how it looks. And if I like the way it looks, I will freeze it and push it down QA.
Okay, so that, yeah, that was a good example of unsupervised learning, having the boxer learn automatically by playing all the other boxers.
Yes, yes. Another note about supervised and unsupervised, you can have a system which, let's say, you look at your agent act based on what you train it,
Hmm.
right? Let's say it's playing, running with the ball, it makes passes, it makes shots on goal, and you as a designer look at what agent is doing
Hmm.
and accept, and you have an option either to kind of accept the agent as a whole, or you can have some kind of a tool that will allow you to mark good and bad behaviors and say, okay, I like when you do this and I don't like when you do this. And if you have that tool, you basically have a supervised learning environment.
Hmm.
Artificial contender or any other behavior capture AI solution should operate in two modes. First mode is learning, when you have a trainer who trains your agent to play, and you have acting mode, where your agent acts in hopefully in a way it was trained.
Hmm.
So in our technology, during learning, what's going on behind the scenes? The technology extracts and encodes situation action pairs, the resolution of that process, and when the actual situation and actual action comes to knowledge is kind of a problem in itself. It's we have a module that extracts learning points during the game. For the football game, um, what we end up doing, basically we use the animation resolution that we had. We knew that, let's say we make, if a human makes a movement on the right,
Hmm.
uh, engine picks up a certain animation that runs to the right, let's say for 5 frames. So now we know that for the 5 frames, our solution could be just sleeping. And after those 5 frames, we need to feed another decision, even if the human continues running in the same direction. So we can talk about this in more
Hmm.
detail, but that's just a basic example. Now, after you extract and encode situation and action pair, you update a knowledge base. For our solution, update means update for nodes and arcs in a directed graph, acting graph. And then we update knowledge generalization structures. It all takes time, real time. The idea is if you update generalization structures during learning, then you have a less performance hit during
Hmm.
acting. And going a little bit forward, I should say that our solution for This is Football 2005 should is running under 10% of processing power, which is not that much. Now, in acting mode, we have a situation matching step. This is where case-based reasoning core comes into play. Basically, your agent faces a new situation and it needs to find a similar set of situation in its knowledge to make a decision. Now, when you picked up a series of situations in your knowledge that look similar to what you have right now, the technology goes to the action matching step. So basically you extract actions from your knowledge and now you try to see if those actions are applicable to the current
Hmm.
situation. And this is where case-based planning comes into place. And also we have a rule-based system that provides additional knowledge from the game basically, and heuristics.
Hmm.
And optional, during acting, reinforcement learning comes into play.
Okay, so using a quick example, when I'm matching the situation, if I'm a football player on the pitch and I've got the ball and I'm near the goal, then the closest matching situation might be to shoot. So picking the action will most likely pick the shooting because the planner says, well, that's the intended goal, and then yeah, I guess reinforcement learning in this case wouldn't be required. But if I had to
It'll be
go ahead.
we'll provide more examples when we look at the actual picture of the graph, but
Hmm.
um, the actual planning that we use in This is Football
Hmm.
look like this. Let's say you look at the situation, you're in the middle of the pitch and there are no opponents nearby. You'll probably pick up the cases with the similar characteristics. They'll have a list of cases where you also were in the middle of the pitch
Hmm.
and there were no opponents nearby. And possible you also had some, let's say, closed or open options to pass to. And then uh, after this action matching step, we'll say, okay, I have several options to run into several directions. I can run to the left, I can run forward, or I can stop. And then the planner will start working, and it will try to build action sequences starting from the current one, and it will see if those action sequences are actually executable based on the current situation. Is it possible to make a
Okay.
pass, let's say 40 frames from now on, when you're actually moving to the left? So system makes some assumptions in every game, and in a football the assumption is that every movement you do should end up with something like a pass or a shoot and goal. Otherwise, that movement probably didn't make a sense.
Mhm. Okay, so we will go into more detail
So
in a
things
bit.
like that.
Yeah, I guess this is what you
Yes.
explained here.
Yeah. Let's see. So this like kind of refreshes our audience perspective on case-based reasoning and planning that we use. So the technology provides efficient way to represent instances, store and retrieve them, search for similar instances,
Hmm.
reason based on similar instances, and definitely very important point, operate within real world processing power and memory constraints.
Hmm.
We don't need some kind of a system that is good in research but cannot fit into real PlayStation 2 or PlayStation 3. So what's important when we talk about case-based reasoning is the fact that every action that your agent does, executes, has a reference to a source situation. Source situation, it's a situation where your agent uh,
Hmm.
learned that action. So this is a partial answer to the control issue. And what's good about it, again, if you have some kind of a tool set built on top of your case-based reasoning, behavior capture AI solution, you'll be able to stop your agent at any moment. Let's say you saw a pass that you don't understand or producer doesn't like. You stop your system, and on a computer next to your PlayStation 3, you can see
Hmm.
a situation where a designer did a similar thing. And now you can call up your knowledge engineer and try him explain why your system thinks those situations are similar.
Okay, so that kind of tool is really useful for, well, first finding bugs and explaining why, and potentially fixing them, because you could get your designer to go back into that situation and maybe capture a short segment before and after that shows what you should have done instead of that pass that was a problem.
Exactly, exactly. So the usual answer would be, okay, oh yes, designer will say, oh yes, I did that. I should have done it. I'll provide a different
Hmm.
example. It's a good case. But there are some cases where designers say, okay, I did that, but I did this because I saw this opening player that run on a different flank, and now you don't have that player. And the answer would be, okay, we should get back to the drawing table and add this factor to
Hmm.
our system to take into consideration. But the good thing is you won't have to retrain everything. What you'll do, you'll add that factor to the system and have it automatically retrained, having that factor in mind.
Right. I guess you must be storing a lot of data, so uh, how can you do this efficiently? This must be a particularly challenging process, particularly for, let's say, a PS2 generation game. How did you manage that?
This part of the science becomes an art a little bit. So
Hmm.
you need to have people who have a deep understanding of the game. And they need to help you or your knowledge engineers to understand what factors will be important, what factors will be less important,
Hmm.
uh, and basically you'll do this first step where you'll analyze your data and you'll pick up everything that your system will take into consideration and will throw out everything that your system will not take into consideration. But then you will take to the more important point where you'll try to convert you'll try to convert simple data representations to more compact but more complex ones. For example, you have I'll give a football example. You have positions of all players on the pitch. And if you try to always take all these positions into consideration, you'll definitely have a
Hmm.
huge bloated database of knowledge that you won't be able to process. So what you actually do, you use some state indexes, some status indicators, and heuristics instead of the raw data. So instead of knowing in exact positions of all players on the pitch when you do a movement, what you do, you use an heuristic measurement of the danger to lose the ball during dribbling.
Mm-hmm.
And when you have an action to do a pass, again, instead of tracing all the positions of all the players,
Mm-hmm.
you store the heuristic of that pass being intercepted. So that's part of the answer. And the last portion to it, you preferably, well, very technical answer, you store bits, you don't store bytes, you store bits.
Yeah, so the typical compaction techniques that you use. Regarding the heuristics, are those built by hand? Let's say the probability of a pass being intercepted, is that something that I would have to implement myself, or can the data help here as well?
Yeah, that's a very good question. And this is Football 2005. What we did, most heuristics we did ourselves with the help of the actual game development team.
Mm-hmm.
Um, in a boxing game that we did, we basically took some heuristics from the game itself
Mm-hmm.
because they already had them built in. So when you have behavior capture AI solution, you can always use everything that was done for the, let's say, traditional AI system or what is built in the simulation engine.
Mm-hmm.
But of course, there is another way. You can have a layered learning solution that would learn some heuristics for yourself. And some of the research, I'm not sure if that was the one I listed like 10 slides ago, but there is a very interesting book on Robocop called, I think it's called like Layered Learning and Multi-Agent
Mm-hmm.
Systems. And this is exactly what they propose. They propose to have several layers. And let's say on one layer, you learn heuristic for the pass. On the second layer, on the same layer, you learn heuristics for the dribbling, and then on the next layer, you operate with those heuristics, having more higher level tactical goals in mind. But in my own experience, at least for the games that I personally worked on, it seems like the handcrafted simple heuristics work the
Mm-hmm.
best.
Yeah, Baylor says that that was a PhD thesis by Peter Stone.
But again, it very much depends on your goals and on the game.
Yeah. So that's available as a book now.
Exactly. Yes, and there is this is a book. That PhD thesis got published. It is published.
Mhm. Okay, one last question about performance. The search process. I guess a big part of making that efficient is the whole tree structure and storing not cases as one big list that you have to traverse linearly, but having the hierarchical access to the data. Is that what you need to make it fast enough for runtime?
Okay. Yeah. To make it fast enough during runtime. Again, there are different techniques.
Mm-hmm.
What we have a combination of hashing and our own generalization structure that allows allows grouping states based on the reduction of the dimension
Mm-hmm.
or based on reduction on the granularity of the factors, and that works like really fast because you have you have a built-in runtime generalization
Mm-hmm.
that works, and the nodes on a different level, they also hashed. So I'm a little bit struggling to explain this without the pictures that we have 10 slides after this, but the core is both using a generalization structure together with hashing.
Okay, let's talk about the workflow a little bit, and then we'll get to all these representations and the examples for the football.
Definitely. So developing workflow will basically consists three big steps. First, you need to integrate the actual technology, then you need to develop
Mm-hmm.
the agents for your game. Agents are not universal, of course. There are certain parts to the engine that are universal, but most of the parts of the engine should be customized. And after you have those agents developed, you go to the next step where you train and fine-tune
Mm-hmm.
your agents, and this is a content design that could be done by designers or subject matter experts. Subject matter experts, you can notice this is a terminology that comes from military simulation that we work on now. So technology integration. what it usually composes of is you need to provide means for an agent to get sensory data and to execute
Hmm.
actions, and you need to provide a game situation recording mechanism. I will talk about this mechanism later on, but the idea is if you want your agents to be able to learn offline and you want to be able to trace your decisions back to their source, you'd better provide your behavior capture AI
Hmm.
solution with game recording. But it's usually a straightforward mechanism. You dump all the situation and action data on every frame, and you only need it during the development. You don't need it after your game is deployed.
Hmm.
And during the agent development, what you do the analysis, you do the programming. Analysis usually comprises of selection of important
Hmm.
factors from sensory data. Then you work on game situation generalization hierarchy. As I said before, usually it's just a reduction of number of dimensions and granularity for the factors. And then you also work on game situation
Hmm.
prediction mechanism for the planning. And game situation prediction mechanism, of course, again, if you plan something and you need to look, let's say, several seconds ahead, what you usually need to work with, you'll usually need to work with a situation that will or will not happen in the future. So you need some means to understand what's going to happen in your game engine. And it's in some cases it's a very straightforward procedure. In some cases it's really difficult. So again, depending on the game. For the football, it was straightforward. Most
Hmm.
predictions that we use are just simple predictions using the current speeds of the players, current positions and the ball, and an assumption that nothing will change within the next 2 seconds. But if you need to predict something farther away, it will depend
Hmm.
on the game how difficult it is, and depending on the game, you will either just have a close cooperation with your engine, or you will have some heuristical way to implement it on top of it. Again, I've seen some engines that have that capability built in for other reasons. Ideally, if you had a super powerful machine, you just run your own simulation 50 frames ahead and see what happens, right? But usually you cannot do that.
To what extent is this process of well, figuring out the problem and then implementing something and creating heuristics and representations? I guess the process of explaining football to the behavior capture system, is that an iterative process?
It is intuitive to some extent. In my experience, what's needed, you need two people. You need one person who understands concepts behind behavior capture AI,
Hmm.
like how it works, what it needs, and you need a second person who understands the game really well. So, and with the cooperation of these two people,
Hmm.
you can come up with simple solutions for like what factors are needed,
Right.
what heuristics are needed, what kind of game situation generalization hierarchy is needed. But it is a process. Again, your comment was right. It is a process that usually takes steps and iterations.
Okay.
It cannot be done like during one day.
Right. So yeah, it seems like you spent a lot of time working on the tools with artificial contender, so it shows. So here's a long list of the kind of stuff that I guess you had to consider. So this is where industry solutions seem to be very different than the academic ones, whereas most of this you would never find in academic solutions, or you probably spent most of your time on these.
Exactly. If we just compare the time we spent on the engine itself and on the tools, I'd say 80% is the tools.
Hmm.
So, and the tools are crucial during the development, during the training, during the tuning, and during the marketing. Because when you show your solution, if you don't have the tool set, uh, nobody's gonna just believe that everything's gonna
Hmm.
just work out magically for the new project.
So is this the advice you'd give to anyone working in behavior capture? Just focus most of your time on the tools and make it easy for yourself to understand what's going on.
Absolutely, absolutely. I'd say you won't make no mistake if you, right from the start, you'll start paying attention to the tools as much as possible and think of the tools as being universal, as like as soon as possible. Don't try to develop something and throw it away.
Hmm.
Rather think about it, how it could be used in other projects, on the next project, in a different game, things like that.
Okay, here's a quick diagram of the whole workflow.
That was just a list. Yes, and now we'll probably need feedback. Is those captions are readable for everyone?
You can zoom in, there's a little zoom button, so if you want to browse around and explore
Oh,
this
pretty
diagram,
good, pretty good.
there's a zoom feature. So if you want to give us a quick overview, then people can browse around whilst you're explaining it.
Okay, yes, this is what I want to do. So this picture illustrates a typical cooperation between the game and a set of tools. So the dark green arrows indicate data exchange through files,
Hmm.
and light green arrows indicate messaging between the tools. Um, so during the typical development, most of the tools will be needed, but they'll be needed at, I'd say, different stages of the development. This particular diagram shows most of the tools in action together. So it's kind of the most complex case you can have. Um, so you can actually, like, if you look at the picture, you can throw out parts of it, and it'll still make sense. So as I said before, as I said before, game engine supposed to generate game situation recordings. Again, it's only needed during the development, but it's a vital part for you to being able to actually, yes, so being able to test everything, to tune everything. Um, so these recordings generated by the actual game engine, and here we have this dark green arrow between the game engine. I think it shows the American football right now, and and the actual storage for the game situation
Hmm.
recordings. Then when you have this they have this those recordings generated, you can feed them into the tool that we call AC Game Viewer. So it's on the bottom, right? This tool allows you to view those recordings, and of course some customization of this tool is necessary
Hmm.
to be able to visualize the recording for the new game. So for the football game, we created our own visualizer that draws those red or blue circles based on positions of the players, and black circle for the ball. For the fighting, for the boxing game we worked on, we used a less complicated approach, and we just used a video feed along with game situation recording, and those two feeds were synchronized. So
Hmm.
that tool could just show the picture from the actual game engine in sync with the data that was recorded during that frame. Now, the game engine, we need to go on top again. Let me try to draw an arrow if I can. Oh yes, I can draw it. Can I move it? No. Again, I have the same mistake that I did before. Let me try to delete this one, and I'll be moving my arrow. So, okay, now we have the game engine. And game engine can generate recordings, as I said before, but also the built-in agent that we have in a game engine uh, can generate an actual agent knowledge. So, and this knowledge is needed even after, of course, deployment of the game. This knowledge is what agents actually use to act. But during the development and during the tuning, you can use both game situation recording and the agent knowledge, and then look at what you have using two instances of AC Game Viewer. And what you usually get in one instance of the Game Viewer, you will see a situation that your agent faces, and you will also have a decision that your agent makes based on a situation that was trained before, and also I'm trying to move the arrow. Train before and record it in your game situation recording database. So what this diagram shows, well, it shows many things, but this what I just explained, you can have a session where a game designers played several games and trained your agents, and then you can have those agents play in the role of the designers. You can have those sessions recorded as well, and then you can have a session where you would compare what agents did, and you can compare it with what designers did,
Mm-hmm.
and you could have a complete control and complete understanding of what was going on using a decision-making analysis tool. And also you can see what your knowledge look like using AC knowledge viewer tools. So the idea is, and we usually run like 3 or 4 monitors in parallel in those the most impressive session that you can have. So you have a game engine, you have agent running, you can have explanations of every decision, and you can also take a look at the knowledge and those gray and black circles that you can see, like very small black
Mm-hmm.
and arrow, black and gray circles actually represent game states that were trained. So this kind of illustrates the most vital parts. Mhm.
If you go to the latest blog post, at the
Yes.
top of the screen, you can find a video of the tools in action, and there's going to be some screenshots of the details of what's on these pages a bit later. I think we should move to the next slide though, because it's a lot of detail to go through
Yeah,
still.
let's do that. Yes, yeah. Um, so now we'll switch to the more kind of a scientific view of the behavior capture AI in general and artificial contender in particular. So this slide lists the most important similarities that we have with other research and development.
Mhm.
So what we actually use, we use the learning by experience demonstration technique. What it means is that you have an expert that can show the good examples
Mhm.
of the behavior, and you learn from it. Now we use memory-based approach like many other research, and for our memory-based approach we use case-based reasoning method.
Mhm.
We also utilize behavioral primitives that some papers call them behavior primitives. We use term high-level actions and ideas. You need to somehow separate a atomic portion of every action, and you need to make a decision. Like for the football game, will it be a movement on every frame, or will it be a movement every 10 frames and you need to average it? Will it be a movement on the joystick, of some kind of movement on the joystick, or it'll be a more high level concept of a pass and things like that.
Mhm.
So we also use behavioral observation traces. So observation traces, we call them game situation recording. So that's exactly what observation trace is. It's a recording of what expert was doing, and it's a recording of an action and also recording of a situation. And we also can use both expert traces or exploration traces. Exploration traces are needed during the unsupervised active learning, where your
Mhm.
agent can freely explore and do something, but still you can record it and learn from it, right? Um, we also use the principle of hierarchical learning and layered learning. Uh, to talk about planning, our planning is also like result. Our planning is also goal directed, but a reactive behavior. So you can replan very often, and
Mhm.
you still have the good reactivity even though you have a plan. And there are some elements of the workflow that we use that other authors also explored and published. For example, our system could use a mode that we call designer mode, and that some authors call confident execution mode. And that mode um, is a mode where you train your agent, and then at a certain moment you switch your agent to acting mode, and then every time when your agent is confused and doesn't have enough information to act, it pauses and asks you for more information. So basically your agent is able to continue acting only when it's confident enough to
Mm.
continue execution, and when it's not confident enough it can ask an expert to provide more examples. That's an optional mode in our technology as well. So this kind of summarizes the similarities. Let's go to the differences.
Right, so I'm guessing you recommend all of these things.
Yes, yes, yes. Uh, well, another point of similarity, similar to what other authors mm, kind of describe, similar to what other authors describe as a human-like agents.
Mm.
Our agents use hierarchical organization of knowledge, goal-directed by reactive behaviors, and incremental learning schemes. Differences, as you can see, are structured in 3 slides because we have more differences than similarities.
Let's go through them quickly.
So the first notable difference is our yes, let's go from that quickly. So the biggest difference is our focus on mimicking a human player style. So our focus is mimicking player style, not effective behavior. So that's, again, most papers will, I wouldn't say most, but many papers will concentrate on the fact that agent will have to be effective. And our primary focus is the agent should mimic human behavior and be human-like. The next notable difference is complex domains. So modern commercial video games are very complex compared to some of the examples that many papers use. Even when research takes, let's say, Unreal game engine as an engine, or Quake, or what have you, most research that I'm familiar with, they will concentrate on a particular aspect or will build on top of some kind of an existing system, things like that. In our case, we have to develop an agent from the ground up, and we have hundreds of sensory inputs, hundreds of actions with hundreds of parameters to deal with, and that makes, well, our application usually different from most research that I'm familiar with. Now, our technology is able to learn multiple policies within one training session, um, as opposed to kind of a one scenario. So it's possible to have a designer that plays a football game in a kind of a flexible style, and we should still be able to capture those policies together. Then we have a focus in our technology, in our end results, on end user experience, and by end users I mean both game designers and end users. And another notable difference is a focus on compact presentation and conservative CPU usage. What can we say about goal-directed reactive behaviors? Like, comparing to other, again, research, acting graph that's built automatically is used as a base for the planner, and our planner have a specific behavior capture specific strategy where action sequence reproducibility becomes a goal in itself. And another notable difference is, in most cases that we face, annotated traces are not available. Basically, designers play, agent learn, and agent supposed to act without additional feedback. But it's possible to provide additional annotations, and they can help to make the agents better, but that part is not necessary for agents to behave. And another notable difference is a maximum utilization that our engine has, a maximum utilization of domain-specific knowledge, capabilities that simulation engine can provide, and a broad usage of heuristics and state indexes. Just in case, state index, like the most common example, is basically a matrix determinant is a good example of a state index. You take a complex object and you convert it to a single scalar representation that can tell you a lot.
One more slide and then we're going to an example. I guess we talked about this a little bit already.
Oh yes. Well, another notable difference, when we built our agent doesn't have a global model, it's rather a set of local models. Then another notable difference, actions in themselves, like when a player makes a pass or a player makes a strike on goal, actions are not used as classification labels. Basically, if you take research on, let's say, decision trees, what will happen is you take an action itself, and an action will become a criteria of how to distinguish situations between themselves. Our solution doesn't do that. We have a separate mechanism for situation matching, and the action that user did doesn't play a role in a situation matching step. Well, another notable difference, that is decision-making process divided into two steps. Step of situation matching and step of action matching. And when we have action matching, we have an additional ability comparing to other systems to kind of separate separate sensory data between situations and actions, and provide agents with an ability to focus on particular elements of the situation based on the action that is recorded. So a good example is a pass action. When an agent recorded a pass action, it will pay a special attention to the position of the receiver of the pass. But when the agent recorded a movement action, it will pay more attention to a danger to lose a ball during dribbling and less attention to the positions of the future pass receivers. And the final notable difference is our attention to overall development workflow and the toolset. Toolset play a big role, and in other research it's usually not the case.
Okay.
So let's go to the football.
Yes.
So yeah, these two slides just So for Sony's This is Football, we have been asked to develop an agent that mimics an attacking play of a human player. So basically, I could be a player with a controller, I play in attack, and the agent's supposed to capture that style. And the agent is put in a similar environment, in a complete similar environment to a human player, like a bot in a first-person shooter game. So in our results, AC Agent learns how to play like a human trainer, and AC Agent acts, plays like the trainer, and mimics a human player style. In This is Football 2005, there are different modes of play. There is an attack, and there are also set pieces like corners, free kicks, and penalties. And because of the differences between those, we had to develop slightly different versions of our agents for each of those modes. So there is a agent for a normal attack, there is a separate agent for corners, separate agent for free kicks, and separate very simple agent for penalties. I guess it's the same for every other game. Depending on a game mode, you might need to have a different analysis behind it. So in This is Football 2005, the actions that our agents learn are dribble or sprint with a ball in any given direction. And by any given direction, I mean not the, let's say, 4 or 8 directions, but I think we have something like 64 or 128 different directions. Then players are able to do ground, header, chip, or long air passes from player A to player B. Then there are shots on goal with a set height, power, and direction. And there are also special moves that player can do, like special skill moves, twisty turns, shimmy with knock-aheads and step overs.
I'm curious to what extent you had to develop new heuristics and new representations for each of the different modes, like in the normal attack or for a corner, I guess you'd need lots of different information for how to perform that particular skill. Was that done as a separate representation?
Yeah, it was done. It was done as a complete separate representation. It was like a complete different agent. We shared some heuristics between the two agents, but in
Mm-hmm.
most part they were different because the set of actions was different and a set of factors that you need to take into consideration was different. And because of that, let's say if you make a free kick, you pay more attention to what's going on in the box area to any other areas, and that area is usually much more crowded comparing to the normal
Mm.
attack, and you need to have a different resolution because of that. So that's basically a separate agent with a separate set of heuristics.
Okay, so that shows the process, I guess, that you went through for applying this to football. Maybe we can go through this quickly again.
This picture is more or less universal to artificial contender, but I will explain some blocks using a football as an example. What it does, this picture, it shows, illustrates data flows for learning and acting modes of EC agents. So basically what you see in the green box is utilized for learning. What you see in a yellow box, it's what's utilized in acting, and there is certain intersection for blocks that use both in acting mode and in the learning mode. So I'll briefly go through the blocks and try to provide some examples. So uh, let me try to make this picture bigger a little bit. Well, I have difficulties to read it myself. Let me try to I'll zoom it in. By the way, when I zoom it in, do I zoom it in for everyone or just for myself?
No, it's just for you.
Okay. So let's go through the blocks. So first we have external game situation. So basically that's all the data you have, all the factors, all the parameters of your actions, and this is what's supposed to be recorded in a game situation recording if you have that capability and if you want to use the tools.
Mm-hmm.
Now, all that raw data go through the module that we call situation adapter. What it does, based on the game you're working with, the situation adapter will pick up the factors that are necessary for further artificial contender analysis for your particular
Mm-hmm.
game. Now, the situation adapter is usually simple. What it does is just picks the data that's needed and throws away data that's not needed and does some simple conversion. Now we go to the game events analysis. That's more important. Depending on the game events, you might even need to switch the agents or kind of do some special pre-analysis. Let's say that it was a switch between attack mode and defense mode, things like
Mm-hmm.
that. And then after game events analysis, you eventually oh, I'm sorry, I actually did a mistake. Game events analysis is an important block. It will make more than I just said. It will convert the like a simplified external game situation to more internal AC game situation that
Mm-hmm.
will already have some kind of a non not simple analysis built in. Now you have a AC game situation, and during learning you will go to action extractor. What it will do, it will extract an action from a situation description, and it could be a simple process if your engine just provides you an situation and action in a simple way, but it could be a difficult thing if your engine doesn't provide you with that for some reason, or your level of abstraction is
Mm-hmm.
higher when what engine could provide. For example, we work on another soccer game, and in another soccer game the situation was much more complicated than what we had in This Is Football 2005. And what we had there, basically there was no layer that could provide us with information on high level action. There were just joystick movements, and we had to somehow divide the fact that pass took place just by analyzing the game situation. We practically didn't have a notion of the action. We had to kind of analyze it, extract the data. And it's, of course, can happen for other games as well, or it could happen in a situation where for some reason actions that designers do are not the same comparing to what your agent's supposed to do, but it's well, it's not a desirable situation. Then what would action extractor do? Action extractor will extract the action from situation and will provide learner with the concept of high-level action. So in some cases it could be as complex as I described, where you had a pass but the engine didn't provide you with that information and you had to kind of figure it out yourself. But even if you had that information, you might need to kind of decorate your action with additional information. For example, you would attach a danger estimation to your movement action. You will attach a different danger estimation to your pass action, etc. And then what you'll have, you will feed that high-level action and AC game situation to learner and game situation classification and encoding module. And game situation classification will work on more complex kind of internal heuristics, and it will convert like we'll do more analysis to your data, and finally we'll create a compact representation of your situation that could even be hashed. And then learner will get that information from game situation classification and encoding module, and it will add a high-level action information to that situation, so you have a pair, and that pair will go to the knowledge.
Okay, so that's creating the mapping from situation.
Does it all make sense so far?
Action. Yeah, I think that to sum up, I guess that's what you're associating high-level actions with specific situations in the game, and you're storing them inside this knowledge base. So I'm guessing the runtime part does the same thing, but it just does a lookup instead of a storage inside this database. And
Exactly. What's important though, we store those pairs, but as you know, they are stored in a graph, so they all kind of connected. So you kind of store the story of the game, not just situation and action pairs. And then during acting, as you can see, the process will go a different way. It will go through a decision-making module, which will not update the knowledge, but instead will take information from it. And then the AC engine will generate high-level action that will go to action executor module, which could be very simple, but depending on the game could be very complex. In a soccer game, in This is Football 2005, it was in most cases straightforward. But what it did in some cases, we kind of we say, okay, we want to run to the left for 7 frames, and what it means, we create a series of low-level actions that run for 1 frame for 7 frames, right? So, but for some games it could be more complex. We have our own internal demo for real-time strategy, and as you can imagine, it could the conversion from high-level action to low-level becomes much more complex there. For example, you move all your units to the left. That's your high-level action, and it gets translated to the actions for every single unit.
Okay, so this part would be the classic AI. Let's say you'd need a low level of the traditional AI layer to decode these actions. Okay.
Yes, and at the end we produce a low-level action, which in most projects we work on, this action is something that is very similar to what human can produce with a controller.
Okay, let's move on to the next slide then.
Well, in most examples, it's supposed to be absolutely the same to what human can produce with a controller. Now, so there'll be 3 slides where I'll try to briefly describe, provide more information on knowledge representation. So this picture just shows a basic low-level data representation in the form of a directed graph. As you can see, we have states and we have transitions between states. What is slightly different comparing to other systems, to some of other research, and even like what looks kind of different on this picture comparing to other pictures, you see circles and triangles. So what's important is that you store information about situations in circles, and you store in some cases a lot,
Mm-hmm.
information about actions in triangles. And all of that information is important. The information that you store in circles takes in place when you do this situation matching
Mm-hmm.
step, basically when you try to find the right subset of circles on this graph. And then when you go to the action matching step, you utilize information in triangles to the maximum. So again, if we talk about football, what do we have? We have in this again, I'm trying to draw an arrow, and let me try to do this. So as I said before, for the football, the example was very much low level. I'm trying to grab an arrow.
I'll put it here.
I can't grab it.
You can.
Just okay. Yeah, oh, I did it. Okay, all right. So, so what we'll store in a circle? In a circle, there'll be description of the situation, positions of your players, danger to lose the ball during
Mm-hmm.
dribbling, time, score, things like that. And in a triangle, you'll have an action like a pass from your current player to player number 8, and additional information about the position of the player,
Mm-hmm.
danger to lose the ball during that pass to that player. And as you can imagine, if I said we record the data 5 times a second, then uh, you'll get thousands of those circles and thousands of those triangles after, like say, 15 or 30 minutes of play. But our compact representations ensures that even after, let's say, 40 or 50 minutes of play, your data could be stored in a size of a few hundred kilobytes. By few hundred, I mean 200, 250, 300 kilobytes. The whole technology for This is Football 2005 was stored under 1 megabyte. I mean, code, data, everything. So let's go to the next picture.
I've got one quick question about the structure of the graph, and it seems to me
Okay.
like if you have a really complex world, the chance of one situation occurring again in multiple different situations would be very rare. So your whole capture would end up being more like, let's say, either multiple individual lines or maybe a tree starting from the same situation. So how frequent are these interconnections between nodes, like from this situation up to this one? How frequent is the graph structure actually used compared to just a plain tree that expands over time?
This is an excellent question. It very much depends on the level of granularity you choose for your lowest level of representation. If for some reason you say, I want it to be very like a very low level in terms of level of details, that's exactly what will happen. You will have those separate lines, and there'll be only a few intersections.
Mm-hmm.
An interesting note that what I noticed during research and a lot of development we did for the games, um, the higher, um, more details you have, the better on the lowest level of
Mm-hmm.
detail. But what's important, we have a generalization structure on top of this, and if you apply generalization structure to this picture, you will have a picture with much more intersections. Let's
Okay.
go quickly 2 slides ahead.
Two
It'll be
slides or one
easier to
slide?
explain it.
Okay, here we go.
2 slides. 2 slides. Uh, so we don't store data in this way, but you can kind of mentally view our data in this way, and then we have some tools that allow you to view our data in this way. And basically you can see it as several layers, where on the most detailed level you don't have many intersections, but as you go up your hierarchy of generalization, you have more and more intersections, and more states
Mm-hmm.
are kind of collapsed into one, and because of that you have more intersections. So answering your question, on the highest level of detail, in most projects we had, we have only a few intersections, but when you go up the hierarchy, you'll get a
Mm.
lot of intersections, and that's a good thing.
Yes, it seems like you could. Well, when you have intersections, I guess you could reuse two different courses of actions. I guess the advantage of having a graph is that if there are two
Yes,
different
yes.
ways to get to a situation and two different ways to come out of it, then your AI has the choice of doing both of those things. So having this kind of graph connectivity is a good thing.
Yes, and well, another important purpose of the generalization structure is to be able to do those searches and analysis runtime.
Yeah. Okay. So let's talk about this a bit more.
So you don't have, if you have thousands of states, you will not be. Uh-huh. Yep. So this picture again talks about generalization. So what we want to say is that you have those circles, and those circles indicate the states on the lowest level of abstraction. And now you have those pink boxes that kind of indicate the potential generalization that can take place when you go up, let's say, one level in your generalization structure. And those states are look similar on that level. And then you have also those blue and green and dark blue boxes that indicate another possible generalization that can happen when you go even higher on your generalization hierarchy. So the idea here is that when your agent looks at a situation, when it can find an exact match is good, but when it can't find exact match, it will kind of consult a bigger
Mhm.
box and will get more states that's similar, and then they'll pick actions from those states, and then we'll go to action matching step, and we'll try to execute the planner and see if it's possible to execute a combination that starts from a certain triangle, and is it possible to match all the factors that are in the triangles. One important thing that is, I think, important for every behavior capture AI system, if you have an heuristic, it is a good idea to apply it in a non-intrusive way. By non-intrusive, what I mean is you don't want to apply some synthetic rule. You want to apply some rule that is very, very generic. And when we talk about football, the generic rule that we use that could apply for probably every game with a ball. If you made a pass and that pass had a measure of being intercepted, let's say it had a measure of average, it was an average danger of that pass being intercepted. Then when you do an analysis during acting and your system says, okay, I want to do a pass, and then you measure danger, and that danger says, okay, now it's not average, it's safe, or it's even
Mhm.
like very safe. Then if the danger is less than it was during acting, then you want to do that action. But if that action the danger is higher when it was during training, you don't want to do that action. So it's kind of a general consistency rule that you apply, and you say, I want to do it if it's safer when it was, but I don't want to do it if it's less safe when it was. But you don't have a rule that says, I want to do it only when it's exactly to the same, has exact level of danger when it was when you trained. But you don't want, and what you also don't want to do, you don't want to have more complex rules where you kind of apply something which is not as generally applicable. And if you have those like less generally applicable rules in your system, then what you end up with creating an AI algorithm instead of doing a behavior capture.
Okay, so using a quick example, at the top we might have a kickoff here and then different possible ways to kick off. And so at the low level, all these would be passes or running actions. And so all these ones that are drawn here were the ones that were captured. But if I have a new situation that's happening during the current game, it might end up somewhere over here. So during the new game, if it's a different situation, my job is to figure out which is the closest or which is the most similar one to the current situation, and that's what you call generalization, what uh, finding aspects of the current situation that are also present in another situation. So that's grouping or generalizing situations together, and that helps you figure out what action you should take.
Absolutely. Yep, yeah, everything is correct.
Okay, and so to what extent does the quality of the um, actions increase or decrease based on the generalization? Let's say if I have a node that's within one of these light blue boxes, um, will that make it harder to pick the correct action if there's nothing similar to this particular situation?
Usually the quality drops the higher you go with your level of generalization.
Mm-hmm.
I also need to note that what I described is we call static generalization, and it's static because we use a static data structure that's on top of it. We also have dynamic generalization that also comes into play, and we have a combination of those dynamic and static generalization, and what we end up with, we have like for every game is different, but it's usually like 10 to 15 levels. You can go up
Oh.
from your lowest level of detail to I mean, from highest level of
Mm-hmm.
detail to lowest level of detail, and higher you go, less quality you get. And based on that, we usually have a quality indicator that is shown on the screen during either development
Mm-hmm.
phase or during the confident execution mode I told about before. And when you have a quality, let's say of 100%, that usually means that you found a match
An
on
exact
a
match. Okay.
highest level of detail. And when you have a quality indicator of 10%, it means that yeah, you have you end up running on the lowest level of details, and it's usually a bad sign. Again, answering your question, more details you have, higher quality you'll get.
On average, would you use all the levels in the tree? Like if you said you had what 14, 17 layers in the tree, on average, does the system manage to, let's say, maintain
Yeah, something like
uh,
that.
how close to the bottom does the system manage to stay in practice?
Yeah, that's also a good question. Again, it very much depends on the implementation. Uh, for the football, for the boxing, uh, for some reason, the system that we built usually mostly stays on a second or third level, mostly, and it almost never works on the highest level of detail. But it also very rarely goes higher than, let's say, fourth or fifth
Mm-hmm.
level, and that's usually a good sign. So that's how you usually measure it. But you can also have, let's say, you can have some kind of a normal, let's say, Euclidean measure for game situation similarity. You can apply it along with your kind of a level of hierarchy similarity measure, compare the two, and during the development kind of come up with a very good level of quality measure.
Okay, let's talk a little more about the zoom levels. Are the zoom levels different than the generalization levels?
Zoom levels represent a static levels of generalization, if that makes sense.
Mm-hmm.
What we do dynamically, we cannot draw a picture like this. So the picture like this could be drawn only from a static generalization. Static generalization usually done by, as I said before, reducing number of dimensions and reducing the granularity. But you can also have some dynamic variations that are not considered zoom levels.
Okay, so the zoom levels allow you to, let's say, simplify all the information that you take into account by saying instead of storing all the information for four players around me, I'm just going to store the idea of a threat level. And so the higher you move up in the zoom level, the more tactical, maybe even strategic information you're taking into account. Is that correct?
Absolutely. Yes, that's absolutely correct. I'll provide a couple of more examples. You say on your level zero, first and second, you can have a name for your player. Like it could be David Beckham, and only David Beckham to which that knowledge applies. But on level four, you can say that this is just a midfielder. And on level five, you can say it's just any player. So when you reduce personality this way, but you also, of course, increase the
Mm-hmm.
generalization. And if your system controls David Beckham and it knows how to behave in this situation as David Beckham, it's great. But if it doesn't, it just switches to the level of just a general midfielder.
And so these zoom levels, I guess, they must be partially manually built. Is that something that a programmer will create during the development?
Yes, yes, they are built. Uh, They are built manually, usually by knowledge engineers together with designers who want to make their input. Let's say a designer plays and
Hmm.
say, okay, when I play, I don't pay attention to this at all, but I pay a lot of attention to this. And well, in some cases, you can have you can easily have different configurations depending on a designer or an agent. Let's say you can have, okay, for designer Mike, we will have these and these factors. For designer Peter, we will have these and these
Hmm.
factors, and depending on a knowledge base, we will load up different factors.
Let's talk briefly about the reinforcement learning. I guess we've already discussed it quite a bit before, but just to give people a quick idea. Um, so the reinforcement learning is the process of helping select the action. So it doesn't help with the state selection or the situation matching, rather. It's more of the process of picking a good or a bad action, depending on what you want. Is that correct?
Yeah, that's correct. One note that I will well continue repeating just in case. It's an optional module. It's not needed at all for behavior capture, but it's needed for introducing adaptive features to the agents, or to do things like tweak a difficulty level, or um, kind of create an adaptive agent that will become better when it plays. Um, uh, what's kind of significant, or I don't know, what's good good about the combination of solutions that we use. um, the knowledge representation that we have on this lowest level of abstraction could be very naturally combined with the concept of reinforcement learning.
Mm-hmm.
As you can see from this picture, all you need to do, you need to assign a certain weights to certain nodes, and then propagate those weights like up through this structure, and color or
Mm-hmm.
reweight those nodes accordingly. So, and it could be very easily done. And how do you pick the good notes and bad notes? It's also kind of simple. Like if you take a boxing game, you just mark your notes according to the health level difference you have between your two states. In a soccer game, you mark special notes where you lost the ball or you scored a goal. When you scored the goal, you mark it as good. When you lost the ball, you mark it as
Mm-hmm.
bad. When you made a shot on goal and didn't score, you mark it as like
Mm-hmm.
semi-good and things like that. And then what you do, you propagate those weights. And now what you can
Right.
do, you can use weights during action selection mechanism as a criteria of more or less importance. And you can either say, okay, if you have several actions to pick from and they all come from a similar level of generalization, then I will pick the action with the highest
Mm-hmm.
weight.
Mm-hmm.
Or you can even go beyond that and you can say, okay, I want to combine several levels of generalization, and I want to ignore the fact that some actions come from uh, the source of a lower quality, but I still want to gear my preference towards good actions in
Mm-hmm.
terms of performance. So you have all those kind of how can I say, gorgeous. You can turn left and right and say, well,
Right.
what do you want? You want to make less human-like but more effective agent, but or less effective but more human-like. You can do all sorts of
Mm-hmm.
that
Mm-hmm.
those things just by adding another criteria for choosing an action.
For instance, in this case, the red node could be I've just conceded a goal, so that's very bad, so we color it red, and then we move back through the graph to say, well, the
Yeah.
action that was just before conceding the goal was probably bad, and the one before that also, chances are, that led to the one before, and so you could, I guess, with a certain horizon, propagate the values back through the graph so that when you're going forward, traversing the graph, you can then see what the chances of conceding a goal are, and then avoid that by picking a more green path as opposed to a red one. Um, so
Yeah, absolutely, absolutely. What's important again, there is a certain amount of art to this, to the algorithm of how much you propagate, how far you propagate, how do you mix. And again, you can have numerous parameters that would tweak a character of an agent very much. If it propagates very far, it'll be more cautious, or again, will pay more attention to the fact that it can somehow score in the future. Or if you propagate just a little bit, then you will have an agent that doesn't look far ahead too much in terms of the achieving bad or good goals.
Okay, I'm not quite sure we'll have time to go through all of these because it's almost 2 hours now. So I suggest that we open it up for questions if we have any. If you have any parts of the talk that we talked about today, and then just post a comment in the chat window. And yeah, in the meantime, whilst they're typing their questions, maybe you could tell us on what you want to do in the future and where you want to take this technology, Iskander.
Yeah, so a primary group of things we're working on right now is working on collaborative team behaviors, and we already achieved some success on that, working on military simulation. Now we have an ability to control squads as compared to a single player with the ball by running parallel decisions. And what's interesting note here is how we do it is when you train together, you can predict what your teammates will be doing. So you kind of have an ability to pick at other agents' knowledges and use it in addition to yourself, and it's not cheating at all because you're supposed to be trained together. So that's one big thing we're working on, collaborative team behaviors. New applications is a big thing. And by new application, I even mean that the fact that we haven't done like a fully blown first-person shooter yet, and we would really love to if we find a client like that. Um, Capturing behaviors from the real world is a big dream. I would really love to see a solution that would capture actual movements of actual football players on the actual field and then create a computer system based on that, and I really believe that it is possible.
Mm-hmm.
Again, we need strong partners to actually do that. We already picked several companies who capture data, but they haven't captured everything that we need. And in a secondary group, we want to concentrate a little bit more on the concept of layered learning, like learn some things before, some things after, not everything together. Concentrating more on action analysis, maybe have some combination of even like decision trees, or as I think I noticed, I think I said something before about mixed Gaussian
Mm-hmm.
modules. So basically use actions to a certain extent during the situation analysis. And also it would be very interesting, we haven't done anything yet in that direction, it would be very interesting to do some work on automated or semi-automated selection of factors before like manually selecting factors, manually handcrafting hierarchy for generalization. And optimization is always, of course, an important point, because if we could fit the technology into, let's say, 1% on PlayStation 2 and 100 kilobytes, we would have more clients. So that's summarize it all. So do we have any questions so far?
Yes, there's one question about scalability in particular. Have you considered applying this technology to an artificial life simulation where you could possibly have 100 possible actions available? Um, or let's say which part of the system wouldn't scale very well if you had that many possible actions?
That's a good question. The good point for our solution, as compared to, for example, decision trees, is the fact that we have no problem of having thousands or millions of actions, no problem at all. For example, this is Football 2005. If you kind of calculate how many actions you have based on the fact that you can move in 128
Mm-hmm.
directions, or you can make a pass to any portion of the field, you actually have like thousands and thousands of actions. But actions themselves, we do not use them for classification. This is why it doesn't important at all how many actions we have. In terms of scalability, let me think on the question where the system will not scale very well.
I think the problem is you might need lots more data into the system in the first place, so you probably have to redesign your game to allow you to capture, let's say, all possible captures that actually uses 100 actions.
That is usually not a big problem,
Mm-hmm.
at least in our experience. What could be a problem, for example, scalability from one agent to 100 agents. That's a problem because Right now, okay, we fit the technology under 1 MB for one agent, but who would give us 100 MB for 100 agents? And in our work on other applications, we were approached and okay, can we model a crowd behavior, let's say just like some peaceful crowd in some village, thousands and thousands of people, then how would we do that? Do we have thousands of artificial container agents, so we would have some kind of a Muppet master on top of
Hmm.
them, which would basically change the system a lot. So I'd say the biggest question for scalability is the number of agents you run in parallel, how many you can actually run. That's the biggest.
Okay, I think that covers everything. But I'd like to thank you very much for your time, Iskander. It was a real pleasure talking to you, and I've certainly learned a lot from this myself.
You're very welcome.
So I really enjoyed this, and yeah, thanks for your time, and have a great Sunday. Cool. Well, have a great day. Ciao, guys.
You too. Thank you. Bye bye.